Good afternoon. My name is Doug Kavner. I'm the Dean of the Eberly College of Science, and I'd like to welcome you to the 2018 Eberly Family Distinguished Lecture. This series of lectures was inaugurated in 2001 to celebrate the 10th anniversary of the naming of the Eberly College of Science in honor of one of its benefactors, the Eberly family of Uniontown, Pennsylvania. I'm delighted today to honor and introduce to you today's distinguished speaker, Dr. Weiss, Professor Emeritus at Massachusetts Institute of Technology, MIT. As you all undoubtedly know, Professor Weiss shared the 2017 Nobel Prize in Physics for decisive contributions to the LIGO detector and the observation of gravitational waves. Professor Weiss is a co-founder and an intellectual leader of the exquisitely sensitive laser interferometer gravitational wave detector known as LIGO that led to the breathtaking and direct observation of gravitational waves in 2015, 100 years after Albert Einstein predicted their existence. LIGO is now routinely detecting these tiny ripples in the geometry of space-time and has launched a new era of gravitational wave astronomy, giving unprecedented insights into cosmic events, such as the merger of binary black holes and binary neutron stars. Apart from the Nobel Prize, Professor Weiss has received numerous scientific honors and teaching awards. Too many for me to enumerate today. He's a member of the National Academy of Sciences, a fellow of the American Academy of Arts and Sciences, a fellow of the Association for the Advancement of Science, and the American Physical Society. He is also a recipient of the Guggenheim Fellowship and the Einstein Prize of the American Physical Society. Without further ado, please give me join me in giving a warm welcome to Professor Freeman Weiss.
Hey, thank you. Thank you very much. Wow. Well, thank you for inviting me. That's important. And it's nice to see so many people interested in this somewhat nutty field, I have to say. And we may not be able to do everything we want to do here because we had to change computers, and so you may not get everything that I had in this thing, but let's see what happens. So let me start by giving you much of this is a little bit of pedagogy. And the reason is that not everybody knows everything about this. You, in high school, and some of you here in college have learned about gravity through Mr. Newton. And that's a wonderful theory, and when Einstein went to Berlin for the first time, and he was brought there from Prague, Germany, from Prague, Czechoslovakia, which didn't exist yet, this Czech part. And he came to Berlin and worked at the Kaiser Wilhelm Institute. It was a big deal for him. But he was told not to work on gravity. Why? Because it was uninteresting. This guy had it all right, but why bother messing with that theory? And you know the theory in this following sense. I'm not going to do any more to just tell you a few things. The gravity is the way Newton had it, the significant part of it was the fact that Newton established that gravity that you experienced on the ground also worked in the heavens. And that was the big jump. The fact is that it was universal. And that was a new idea at the time, that somebody on the ground, something you explained on the ground should also work in the heavens. That was a very dramatic thing, in fact. But what was it? It was a fairly simple idea. The idea is that there's a force between two masses. That's one of them. That's another. You two neighbors next to each other attracting each other, and with a constant, which we'll not worry about. And but it gets weaker. The force gets weaker as the square of the distance between you. And that explained not only the two of you attracting each other. Well, there are other reasons why you might attract each other, but physically that way. And the thing is that it also explained the moon around the Earth. It explained all the motions that people knew at the time. And then later on, it also explained almost everything, but it got into trouble. And it got into trouble with one planet, the planet Mercury. Planet Mercury did not seem to obey this completely. In fact, planet Mercury, and I'll tell you what it was doing, it was going around the sun. If it was all by itself, without other planets around, it would go around in a lovely ellipse, and that ellipse would stay fixed in space. It always would go around the same way. But what it does is it doesn't do that. It begins to precess, meaning if the ellipse starts changing direction. It does it very, very slowly, but it was a problem. And so people began to look for another planet that might be between the sun and the Earth. Because that could, or sun and Venus, really, and that might explain this, but they even gave it a name. I mean, imagine if people do that sort of stuff. And they gave it the name Vulcan. And they kept looking for Vulcan. It was very hard, never found it. And so what happened is Einstein knew about this, and here's Einstein. And he had a new way of thinking about gravity, which was a geometric theory. What his theory had, and I'll give you an example of it in a minute, but it's an equation which says something completely different. It says somehow the way you measure things in space and time, that space and time on this side of the equation, has something to do with the distribution of matter and energy in the universe. In other words, there were no longer any gravitational forces. And the reason why that was so important to him was that because it allowed him to add some new things to the Newton theory, which were the following. First of all, it allowed him to say he could calculate the orbit of Mercury around the sun. He had it right on the money. And in fact, he got it so well that he couldn't sleep for a week after he discovered that. And then what happened is that it also allowed him to deal with bigger masses and very fast masses, which was not something in Newton's theory. And the other thing it added was a news function, a function which allowed you to have something happen over there and not do something gravitational over here right away. There was a delay. And that was very important, because if you had the Newton theory and you interpreted it that way, you would have had information traveling from one place in the gravitational field to another with very much faster speed than speed of light. And that was established somewhat earlier by Einstein to be the limiting speed. Don't worry about the comic books. They're wrong. Okay? You can't go faster than the velocity of light. And the thing was that that became gravitational waves. And so here's the image that you want to have. This is just an idea you want to have when you think about Einstein. What it is think of a great big jungle gym. How many of you people have ever played in a jungle gym? I think most of you. Oh, good. Excellent. And so think of a giant jungle gym. You laid out the jungle gym, all the bars and everything, and now you take a cut through the jungle gym, a two-dimensional cut through the jungle gym. That's what's in this picture. But now what you do and what happens is here are all the crossings of the bars. And in this picture, they're not there, but if you drew them in, you would find if you put clocks everywhere, there's an intersection here, all the clocks where this thing is sort of flat looking and way away from this object, which we'll get to in a minute, they all keep the same time. And now what happens is you put the sun, this is what's supposed to be, into the system, and you'll notice two things. Well, the big thing you'll notice is that now what happens is the space actually gets distorted somewhat. In fact, it gets curved a little. And here's the Earth with its little tiny effect on the space-time. And the thing you don't see, because I didn't put it in there, is that the clocks in here, where the sun has already bent the space, the clocks go a little more slowly. The clocks go more slowly in a gravitational field, big, strong gravitational field. And those two things, space being distorted, time being distorted, was the basis of the Einstein theory. And then how did motion happen? Motion happened by noticing that these two objects do this, and they bend the space, and they travel in the shortest path in space and time together in that. There's no more forces. Space has determined how things move. And that was a very elegant idea. And took many, many years for people to even begin to appreciate, because it was so hard to do any experiments that would demonstrate this. What? No, I have what? No, I'm supposed to be doing this without this. Hold on. This does not work? I'm surprised that it does that. Okay, I better stand still. Okay, so here's a gravitational wave, and I want you to understand it. And it's, first of all, Einstein predicted this in 1916. He had the theory that I told you about in 1915. And then he made a mistake in that theory, which we'll get to. But he had a lot of it right. And in the theory, what happens is that the gravitational waves, the sources of them, are still the same kind of thing as in the E&M, accelerations, but in this case, accelerations of mass. Where they're accelerated masses, they might radiate gravitational waves, but it's not every motion that does it. It has to be a motion that is not spherically symmetric. So if you blow a balloon up and let it collapse in its nice sphere, it will not radiate. But if it's something that's going around in an orbit, that'll radiate. Or if it's going from being an ellipse that's to a circle and back to ellipse, that'll radiate. And so what does this wave do? First of all, it propagates at the speed of light in the theory, so it goes, it's the same as light. And it's called a transverse wave. It's a wave that does its dirty work, transverse perpendicular to the direction in which it moves. And that's what I want to demonstrate to you, because you won't understand how the detector works unless you understand this. So I want to look at you to see if you follow me, okay? And so here is, I'll get this thing moving in a minute. Imagine that you're standing where that red dot is, right there, a red square. And now I've sprinkled masses all around, very light masses. And I'll turn this on so that the gravitational wave is actually doing something. Let's see if it actually behaves itself. Oh yeah, let's just see. This is where the PC makes a mess out of this. But okay, let's have to look at this jagged motion. I'm sorry about that. It would have been different on the other computer. But still sort of works. You'll notice something interesting about this picture. You'll notice that in one dimension, this is that here the gravitational wave is coming at you or going into it. I don't care. But here's what's going on perpendicular to it. These dots are moving, some which are moving, they're both moving away. In one dimension, they're moving away from each other, while at the same time, in the other dimension, they're coming toward each other. In other words, space is being stretched in one dimension and contracted in another. I'm sorry this is so jumpy. That has to do with this computer. But the thing is that I hope you get that much, right? You can see that? Yes or no? Some of you say, no, well, okay. You'll have to either see it for a little bit. But there's one more attribute of this thing, and this is that the amount of motion of the dots. Let's take a look at the ones that are very far from you. You're standing right here, and the ones that are furthest from you are moving a lot. Like, see how much they're moving? They're moving a lot. But these guys near you are not moving very much. And that is there's a constant in this, and that constant is called the strain. The ones that are far apart are moving a lot. The change in their position is big, but they're also separated by something big. So the ratio of the change in their separation divided by the distance they were initially apart is a number. We'll call that the strain. And that number is the same for every dot in that picture, every pair of dots in any one moment. And so the thing what happens is then that the gravitational wave causes, I'll tell you, you can do this for yourself. Take a rubber band when you go home, stretch it, and make some marks. Get a buddy of yours to make marks on the rubber band every quarter of an inch. And then you pull the rubber band, and you'll see exactly this motion, at least in one dimension. Okay? All right. So the next big event in this thing is that gravitational waves, right away, Einstein, when he wrote this paper, and I won't bore you with this, I kept to say, when he wrote that 1916 paper, at the very end of it, he said something quite remarkable. He said that there is absolutely no way, and he said in German, a very pedantic German, that there is no way this will ever play a role in physics or science. This whole phenomenon. This is 1916. Why? He said that because the numbers are so tiny, as we'll get to. Einstein had done some back-of-the-envelope calculations and shown to himself, even though that the amount of stretching of space that could come from anything he could think of, whether two trains collided, for example, he found out that the strain from two trains colliding was about 10 to the minus 40. It's a tiny number. Though I better explain the powers of 10 to you. It's important. Otherwise, I can't talk to you. Remember, you can write 10 to minus 40 is sort of a bad way. Let's start with something you know. 1,000. 1,000. You can write that as 1000, right? But you can also write it as 10 to the power 3 because there are 3 zeros. So that's a nice way to write big numbers and very tiny numbers. For example, 0.001 can be written as 10 to the minus 3. Okay? And the people give these names. That's 1,000th. When we get to these very, very tiny and very, very big numbers, the names get so complicated, it's much easier to write the powers of 10. Okay? So bear with me. All right, so it turns out that, we'll get to that, and let me talk more about what this slide is about. Turns out that Einstein made that wonderful statement, and there are two reasons why he made this statement. It was one, because the technology at the time was just not up to it, and that's the real reason he made that statement. He knew enough. And then the astronomy at that time wasn't good enough either. There weren't enough things known that allowed you to measure, for example, something which we're about to talk about here. Because the very first measurement of gravitational waves, an indirect measurement, was made by these two people, Hulse and Taylor, and they won the Nobel Prize in 1993 for doing this. It's this. What they saw was a system. They saw a star which pulses. They didn't see it. They heard it in their radio telescope. And let's suppose the radio telescope is over here, right there. And this is a star that is rotating. It's called a pulsar, and it's a neutron star the mass of our sun, made entirely of nuclear matter, with a density that's unbelievable. It's a tiny star, no bigger than the town you were living in. And so, but there it is. It's rotating around, and it was putting pulses out at about 17 times a second. And that's what they picked up in their radio telescope. But they also noticed a further thing. It's actually the graduate student who noticed this, Holst. That's why he won the Nobel Prize. Taylor wasn't there. He was teaching. Okay. What is that they noted, the data showed that sometimes it was a little faster, and that's because the star was moving with another star around. They were moving around each other, so this is moving around, and it's the Doppler shift, the same thing that makes police cars sound different than when they're behind you and then when they're in front of you. You know, the whoop, like that. Okay, or the other way around. Whoop, ooh. That's the way the police go if they're not picking you up. You see, it gets lower in frequency. They bypass you. Okay. So anyway, the thing is that here what happens is that they noticed that this thing was going. They saw it a little slower here, a little faster there, and they therefore divined that the thing was going around. There were two stars going around each other. Excuse me. Yeah, I see the problem now. And so, in fact, that became a very big laboratory for doing relativity measurements that Einstein couldn't have conceived of. And one of the things they measured was the fact that as these two were going around, is depicted in this picture. This picture is a picture of epoch. This is time from 1970s into the 2000s, and that's the scale in the x-axis. On the y-axis is the time it takes for the thing to orbit once. And that's getting shorter and shorter. Those negative signs indicated that. And those dots that you see here are data they took, and the line that goes through this is the prediction that Einstein would have made using his equations. In other words, and they used Einstein's equations for this. So it turns out what was going on here is this system was losing energy to gravitational waves. They had solved for all the other parts of the problem, and then they found this. And so this was the first really inference about that the gravitational waves existed. The next thing that happened in this history was a man at the University of Maryland, whose name is Joe Weber, and he had the idea, and this all this you can see now, it's beginning to happen in life. It's not your lifetime. This is certainly my lifetime. It's in the last century. It's in the end of the last century. So this is all stuff Einstein couldn't have thought of. And because electronics now existed and things existed that, like, for example, what Weber attempted to do is he decided maybe he could measure these gravitational waves, that stretching I showed you in that picture, and the compression. Maybe that would happen in a great big piece of aluminum. And there you can see him standing there next to it in this piece of aluminum. And what he's doing here is he's mounting strain gauges, little devices that if you're an engineer, you put on things to find out what the stresses are in a system that you've designed. And he's doing that. He's putting them along here, and that whole system gets stuck in that vacuum system right there. And then he closes the door and pumps it out. And so what unfortunately happened to him was that he built 3 of these. He put one in Chicago, and he put another one in Maryland at the university, and then he took another one and put it in a golf course not too far from the university. And he began to see coincident excitations of that piece of aluminum. 3 different pieces of aluminum. And he wrote a paper in 1969, which was evidence for the discovery of gravitational waves. That's what he thought was going on. And what happens in science when somebody makes an astounding claim like that? Every other scientist who has time or interest says, can I do an experiment maybe that's like his, or maybe better or different, and see if I see the same effect? That's the way you check things in science. You don't accept somebody's word for it unless you're absolutely certain of it, and you can't do anything about it. And so consequently, something like 20 other groups in the world made experiments like this. This was not such a terribly hard experiment. And they saw nothing. And that was sort of complicated. It made the field there were lots of arguments about people that Weber was lying, which is not true. Weber made somewhere there was something that was exciting those bars in coincidence, which is sort of amazing. And I have ideas what it might have been. Thunderstorms is what I think did it, but never mind. He never agreed to that. He's now dead, unfortunately. But the thing is, what came of it is that now we know that those particular detectors had a strain sensitivity, a sensitivity which was not adequate to even get approached detecting gravitational waves. Order 1 million to maybe even 10 million to poor sensitivity. And so the next thing is another idea that then came up was to do it with measuring the time it takes light. Now this one I want to explain, and this is the basis of the LIGO measurement. What it is this. This is, again, I hope, a working demonstration. I mean, it may not work, and then I'm in trouble, but we'll see. This is a laser. It doesn't look like a laser, but it's a laser. Here's a beam splitter, a device that passes half the light, goes out, goes through it. When it gets hit by light, half of it gets reflected. And this is, by the way, if you want to relate this to the picture of the dots, and you want to think of a gravitational wave coming down on this, think of that as the place where I put the red square. That's you. And then you're the very distant dots that were moving a lot. That's one of them. And then there's another. These are mirrors. And now what you're going to see when I turn this on, let's hope it works, is, maybe do something. Okay. Yeah, what you see is a laser putting out light. This is the electric field in the light. This is inside the light. But the red is where the light is, the light power, the thing that you can see is. And you'll notice that if these two paths are equal, that one and that one, the two waves cancel each other from the beam splitter to here where there's a photodetector. There's no light going to the photodetector in this setup. Okay? And so what happens is now you bring a gravitational wave down, it stretches one of these arms, and it compresses that arm, and you notice there's light going to the photodetector whenever the arms are not equal length or equal time. That is, in fact, the basis of LIGO. There is no more than that. Okay? How many of you got the idea? How many didn't get the idea? Well, nobody will admit to it. That's the trouble. Okay, it's an old problem. All right, thank you. So, okay, we got past that one. And, all right, so now comes along Kip Thorne, and he says, you know, if you want to do this, you've got to be able to measure a strain. That's Kip Thorne as a young man. And Kip Thorne is one of the Nobel people, okay? And the other one was Barry Barish. And, but Kip has been thinking about this for years and years. And so he told us all that if you want to measure an H, which is a strain, here, a change in length divided by the distance between 2 points, that's the change in the distance, and that's the actual separation. You've got to be able to measure as an H of less than 10 to the minus 21. Okay? We'll get to what that means in a minute, but that's a very, very small number. And if you turn out, and that's what the dean was talking about. And so here's another place where this is supposed to be an approximate sign, but the change in length then is they're dealing with two gigantic factors that you have to fix as an experimenter, because you have to make a measurement of length that's 10 to the minus 12, or 1 million times a million times smaller than the wavelength of light. That's the first problem you got. So you can pick out these very small motions. And the other thing is you've got to make sure those mirrors in that picture don't move for other reasons besides the gravitational wave by about 1 millionth times a millionth. Because you and I are sitting here in this room and we're moving up and down because the Earth is shaking by at least 10, maybe 3 or 4 wavelengths of light. So consequently, there are two big factors that you have to solve to make this happen. And one is on the sensitivity of measuring the position very carefully, and the other one, you got to make sure that the thing that you're looking at isn't being jiggled by something else. That was the challenge. And so I think I will go through this. This is a thing that is just a matter of giving you a little better feel for what that number is. So if you take a meter, which is about 3 feet, and I wish we had meters in the United States that everybody used, but the car industry would never let us do that. And okay, you go with a meter and you go down to something you can still experience is the size of your hair, and you've divided by 10,000. So you're down to 10 to the minus 4 meters. Okay, and now you divide that again, and that's something you can measure easily. You can also, if you go to the wavelength of light, and you're down to 10 to the minus 6 meters, you have to divide another 100. And that you can experience on your own, and you'll do this tonight when you look at a street light that is yellow, if you can find a nice yellow one. Look through your fingers, and you'll see little bands. When you squeeze your fingers together as you look through them, you will see little bands. And if you do a little arithmetic, you will find out that that's the number. No, it doesn't work in this place. I'm telling you, you got to use light that is yellow, or what I'm asking you to look at is a sodium light. And I'm sure they use them here. Okay, so, all right, but you're not there yet. We got a long way to go. So next thing is you go down another 10,000, and you get to the size of an atom, which is about 10 to the minus 10 meters. And you can still prove that to yourself. How many of you have ever done that, by the way? Nobody in this room has ever proved to themselves the size of an atom? Oh, boy, what a wonderful experiment you have in store for you. Let me tell you what you do. What you do is get a medicine dropper, put a little oil in it, and stick it in, measure the diameter of the drop that drops into a great big bucket, make it your bathtub. Fill it with water and sprinkle some chalk dust or a little bit of dust or flour on the water. And let the drop go into the water. And then you'll notice it goes whoosh, and suddenly you get this nice clear spot in the water. Go and get your tape measure, measure the diameter, measure this size, measure that size, multiply them to get the area. That's good enough. You don't have to do any better than that. And then you say, okay, we have this conservation law here is that the volume of that spot in the bathtub, which means you want to know the height times its area, that's got to be equal to the volume of the drop that you measured to begin with. And the unknown in your little experiment is the height of the water, the height of the height of that region where the water is clear in the bathtub. So you solve that equation. The volume of the drop is measured from the medicine dropper, divided by the area of the bathtub that got cleared up, and that number will be the height, and that will be about the height of an atom. It's an interesting experiment to do. You won't be off by more than a factor of 2, maybe 2.5. Okay, for most small atoms. So anyway, you can still do that one on your own, but then you got to trust me for the rest of it. So this is the next. You still have to divide by 100,000 to get to the size of a nucleus here at 10 to the minus 15 meters. And that's still not enough because you have to get to 10 to the minus 18, so you go down to 1,000th the size of a nucleus. And that sort of gives you a feeling for what the problem was. Okay? All right. So how was it done? It's done in the following way. So you recognize this picture, and I'm not going to show you everything in the picture, but I just want to show you the essential ideas. Here is this place where you have to get that factor of 10 to the 12 in going from the wavelength of light to what you need. And here are the various tricks you have to pull. So here you recognize that laser you saw in the animation. There's that beam splitter, and there's that distant mirror, and there's the other distant mirror. So you'll see some other mirrors in here, like this one, and that one. What do these guys do? These are partial mirrors. These are mirrors which reflect, let the light go in and let the light bounce back and forth many, many times and come back out again. The same thing on this side. So effectively what you've done is you've increased the time of the light interacting with the gravitational wave. That's what you've done. But you make it so the time is still the same, so that when you go over here, no light is going to the photodetector. Same situation as you saw in that movie. So you put another partial mirror right in here. This is a very clever idea that was had by Von Drever and the German group. And what it is this, since now, if you put the laser lights going into this, none of it's going to the detector. Where is it all where's it going? It's all coming back to you. That's where it's going. It looks like this whole system is a great big mirror. And what happens is that you now get the following. Here, if this is a partially reflecting mirror, what happens is light comes from here, hits that partially reflecting, and some of it bounces back and goes to the laser. So there's one path that brings light back to the laser. There's also now all this light that you injected, and that comes through this partial mirror and comes back to the laser. Now, what you have to do is cleverly make those two lights cancel each other, just the way you did with the interferometer before. And that's something you can do. And if you do that, you wind up with a very interesting situation. You wind up, let's say, with 10 watts out of the laser, 500 watts circulating in here, and about 100 megawatts or 200 megawatts sitting in there. And that allows you to build up the signal so that you can, and that ultimately gets you that factor of 10 to the 12. I think I'm going to forego this. And the other thing is that we had, in the initial LIGO, with other ideas, we had 2 detectors. And this is now LIGO. There's one in Louisiana, and there's another one up in Hanford, and that's in Washington State. Here, there are 2 other instruments. One is, this is an instrument like the one you saw in that schematic. There's one in Italy, and then there's a research instrument in Germany, in Hannover. And we'll get to these. These are going to be built. These are still in the future. And so when what I'm about to tell you was done, it turns out the only two detectors that were on and with sufficient sensitivity were these two here. Those the two detectors that are part of LIGO. And so I'll quickly, if this works, I'm in good shape. I'm going to give you a little tour of LIGO, very quick tour. Let's hope it works. Yeah, it looks like it's moving. That's LIGO from above in Louisiana. That's LIGO from above in Hanford. And here, these are concrete tubes. Unfortunately, it's too fast. And the light travels in evacuated tubes. This is about 48 inches in diameter. And here's a laser table like you guys have right here. It's no different. I mean, it's just a lot of stuff on a laser table. And this is the control room. And here are people learning how to run running the instrument. And it's interesting, by the way, just for your people who have to make a shift from Mac to PCs, it runs about double the rate on the Mac on the PC compared to the Mac, so that you have got a very short and not unintended fast view of this. Okay, so the very first thing is that when LIGO started operating in this initial detector, which I haven't described everything to you about, what is this? I don't want you to know everything about it. I think the important thing to show you is that there are a bunch of curves in here, and this is the sensitivity as a function of the frequency. For example, here's 100 hertz, and here's a kilohertz, here's middle C about, right there, 200 hertz. That's middle C on the piano. And you'll notice that, and this is sensitivity in the position. It doesn't matter how well you can measure the position. It translates into strain by dividing by the 4,000 meters. And so here is when it all started. When we started working in there, this was the sensitivity. This gets better and better as it goes down in this picture. And finally, we got down to here. And that's where the thing ended in the initial detector. Here's the design for the initial detector. See that? It's buried in here. You can't see it. But there is peeping out a little bit right there. You can see that we didn't quite make it to the design at very low frequencies. But we got close enough so that people figured that we knew what we were doing. Okay? I mean, all that technology, which I told you about, is in this thing. And we got a result that people on the outside who had to judge us said, yeah, you were able to make this thing work, but we made no detections whatsoever. None. And I'm very proud of the non-detection. Why? Because it was a good non-detection. It was a detection that says, yes, we know what we have, and we didn't see anything, and we could set an upper limit that meant something. That's worth something, too. Okay, so then further improvements were made. Okay, so again, what was done after we got more money was to improve the detector we had, and there were two improvements that had to be made. One was to improve the performance at low frequencies, and that was done by hanging this mirror, which is one of those mirrors, by a quite tricky bunch of pendula. Here's the ground is attached to these springs, here's one pendulum, and that hangs from another pendulum, and that hangs from another pendulum, and finally, here's that mirror. And that's where the one tick that was done, and to improve that second factor of 10 to the 12 that was needed. And then there was another thing I'm only going to tell you about. I don't want you to look at this picture to understand it. It's a platform which holds this device, and there's this multiple pendulum that's hanging from a set of platforms. And I'll tell you what those platforms do. They do exactly what, how many of you have sound-canceling headphones? Many of you have. Oh, good. So it's exactly the same idea. What you do is you have devices on that platform that measure the motion of the Earth with respect to the stars, and then there are pushers on that platform, and you make it so that the device that measures the motion of the Earth you cancel the signal in these seismometers. In other words, you push the platform, so it just cancels the Earth's motion. And you do this twice. And that device, by the way, has use for many other people. And that's why I want you guys to know about it. People who do microscopy, people who do, it's a way of dealing with very, very precise isolation of motions if you have to deal with a noisy place. And that's something we can contribute to the society. Okay, so what did we see? Now I'm going to talk about what was actually seen in the science of what we've seen. This is what we're seeing almost the day we decided to start running this new detector. This is advanced LIGO. And what we're seeing is something that, here's the thing that was seen in Louisiana. Here's the thing that was seen up in Washington State, and it was very important to the whole strategy of the experiment that we had these two detectors. Because with them, you could get two things. You first could get confirmation of what we were seeing in one or the other, and you could also get an idea where it was coming from. And so here, this is noise, You can see they're not the same in this early part. This is time this way, and that's strain. And by the way, here it's about 10 to the minus 21, just what Kip thought. That's the peak right there is around 10 to the minus 21. It was sort of amazing. And then something begins to develop, which is sort of systematic in this thing. And then it gets bigger and bigger, and finally it quits. And this is noise again. And you can see that these two things are quite similar. We can put them on top of each other. And here's what they look like on top of each other. They're no good on here, they're no good over there, but in the places where there looks like the signal, they're within what the noise would allow them to be equal to. They're allowed to be equal. And so that was a very important part. And so here's what it sounds like if you listen to it in, that's not loud enough. Okay, we have a problem. So you're not going to get the sound, the hell with it. Now just you hear it goes, bloop, bloop, that's all it does. But what's being plotted here is time versus the frequency. And so you will hear this again in a minute, or I'll try. This goes sort of from the signal that you see here. This is the strength of the signal in that color. Do you think you have a way of getting more sound out of it?
I'm not sure if there is a...
Yeah, don't mess around because we have plenty of problems. The thing is that this is that waveform, and there is the frequency content of that waveform. And that runs sort of from 30 hertz, that's sort of the beginning band of LIGO, and to just about middle C, 256 is about there. And it does the same, pretty much the same thing at both places. And so that was a big deal. And so what do we, okay, I'm not going to bother. What do we think it was? Well, this picture is another miracle, by the way. This picture is a thing that people here do. And what it is that, and it's worth telling you this because, do you mind if I go 5 minutes over or something? Okay. Well, we'll see. I mean, when people get tired, they walk out. But the thing is that people could not solve Einstein's equations completely. And what happened is that you eventually used computers to solve those equations. They're terribly hard to solve. And in fact, the progress in solving Einstein's equations was almost in parallel with the development of the hardware that made the detections. And that was sort of a miracle because it got done in the numerical relativity a little before the detection, which was wonderful. Otherwise, we would not have been able to interpret what we saw as well as this. But here's what we saw as interpreted by a computer. Okay, what you're seeing here is you're looking down on this thing again. You're looking down on it. We'll get in a minute. And this is, again, taking a cut through space. Here's the waveform down here. But the important thing is here are two black holes, and they're going around each other. And what's designated in this picture is wherever there are arrows like that, that shows you where there's tension. There is stretching and compression of space. And the colors tell you how the clocks have been changed. So, for example, when it's very orange, the clocks are very much slower than they are in the green. And when they get black, they come to a stop. And these two black holes are getting closer and closer. Here's the time up there. And as you'll see there, these are the two things that made that waveform. We saw only the latter part of this, now with the part that they slowed down. And you can see this absolute storm in the geometry of space and time. Because right there, it's black. Look at that. Time has stopped in there. And so there is two black holes, they merge and they make a new black hole. And what's happened is that has caused a lot of energy to go away from the system in the form of gravitational waves. And that's symbolized by these waves that are leaving this thing. So that's what we believe we saw. And I have a very nice story to tell you about what this was all announced in a news conference in Washington in the spring of 2015. I was in New York in this New York City subway about a month after that, and I saw this advertisement. It's this thing on the side. I have to go look over here. It says, "Scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet." Okay? And that was in the New York City subway. Imagine that. And it's unbelievable. And right away after that, there was the same week, there was an advertisement in the New Yorker where it says, "What was that you I just heard? Two birds talking to each other." Oh, or was it two black holes colliding? And if you had heard that chirp, which I was able, you would have understood this cartoon a lot better, okay? Anyway, that's sort of amazing that something would get into the public conscience in such a way so quickly. And that has something to do with Einstein. When I go to high schools and ask people, who do they know as a scientist? It's always Einstein. It's not Maxwell, and it's not anybody else, it's Einstein. And the other thing is, everybody knows about black holes because they're evil and they come out in comic books. So, it's not something that, but they may not know exactly what they do, but they know the word and they have the idea it's bad stuff, okay? So, all right. So here then, what happened shortly after is that there were more black holes we saw. And here's the one now. This is again time, and this is the amplitude and strain. And this is the one that we've been talking about, but very shortly thereafter there was another. This is not as good a measurement. Here was another one, which is a good measurement. Here's another one that was a good measurement. And here's sort of the numbers that go with these. We found, doing this modeling, we found that we had 36 masses of sun in one of those black holes and 29 masses of sun, and 3 masses of sun disappeared into gravitational waves. It's unbelievable. And I want to give you a feel for something about gravitational waves, which I want to give you. The others were different masses. You can read them as I tell you the story. But there's a nice way to sort of feel a little bit about this, understand a little bit about the field if you do the following with me. Take this system and put it at the distance of the sun. I mean, we don't have that, but suppose you put it at the sun. Okay? What would happen? The strain that you measure is 10 to the minus 6. That's zilch. What does that mean? Could you ever tell whether you've changed length by a micro-inch? No. It's zilch effect. It's a nothing. Okay? But what went through you is unbelievable. What went through you is 10 to the 25 watts per meter squared. Now, what does the sun put out and give you sunburns? 10 to the 3, 1,000 watts per meter squared. So this is an unbelievable amount of energy that went through you. And it tells you something. It says that space is extremely stiff. And those of you who like mechanical analogies, it turns out space is about 10 to the 20 times stiffer at 100 hertz than steel. Okay? The Young's modulus of steel. Okay? So it's very, very hard to squish steel. And so anyway, here's another one which is a very important event. This is just another black hole. We're getting sort of blasé about this. But this is last year, and it turns out a very important event. This is now the Virgo collaboration. The people who have that detector in Italy, they saw a black hole event as well. And that allowed you to find out where in the sky it was. And see, how do you find out with only 2 detectors? But you have they're not like the telescopes. You can't point them. The way you find out where the sources are is you found out that Louisiana was hit first, and then Washington State 7 milliseconds later. And that gives you a circle in the sky where the source might be. So you need more than that. And so what happens when you had another detector, you made another set of circles on the sky, and the intersection of those 2 circles with Virgo in it now gave you, instead of 1,000 square degrees of uncertainty, and this is the sky, you got an uncertainty that's more like 30 degrees. Now, when you try to tell an astronomer, go look for this, and you tell them it's somewhere, they look at you like you're out of your mind. Okay, I mean, the telescope is tiny little, but when you start telling them it's 30, they still think, well, you're sort of arrogant. But you're not completely out of your mind. And later on, we'll talk about things which make it so that you can get down to sizes of about the area of the moon. And that's about all we're going to probably ever do. But that is enough so that astronomers can find it. But there are other ways that you can do too, and we'll get to that in a second. So anyway, here are the black holes that were found in a little picture. There are all of them. And people have seen black holes before. This is mass, and this is just an indicator. There's no indicator. This has no axis. But this is the first one we saw, and the next one, and the next one, and the next one. This is the last one. So these are the 2 that started, and this is the size of the guy who ended. So anyway, that's just a nice, pretty picture of all the black holes. Okay, the next big event was something that happened also in that month. And it's sort of unbelievable. We got this incredible thing. In 1 month, we got 2 things that actually changed the field. It was just maybe, and that was all in August of last year. What was found was something quite different. What was found was this. I hope you're with me and being able to interpret these pictures. This is time, and this is now amplitude of, the amplitude is the color in here. If it's yellow, it's louder. If it's blue, there's nothing. So again, now the scale, this is again the same frequency scale. Here's, we'll see it, I have a little trouble to see, it's about there. So there's some of this, here's this signal that lasted for very much longer than the black hole pairs. And it was seen by somebody else, not just gravitational wave detectors. That's the important thing. what we're seeing here, you can see this, this is very high frequency. It turns out we now know what that is. It's two neutron stars of the same kind that I showed you that Holst and Taylor did their initial research on. Very similar to that system. And these two neutron stars have been going around, and they've been losing energy to gravitational waves, speeding up. That's one of these horrible things in gravity. Things get faster when they lose energy. But you'll have to live with that, I'm sorry. So what happens is they're speeding up and eventually they smash into each other. And what happens is that they smash into each other. We're not sensitive enough. That's way up here. In fact, it's about there, not in that picture. We just weren't sensitive up there. Well, we will be. We will get there. And what we're seeing is, here's what we're seeing on the same time scale in a gamma ray telescope, the Fermi satellite. And there's an excitation of a gamma ray burst about 1.7 seconds after we think when these would have collided. And it was seen about two instruments on that satellite, and also on a separate satellite. It's not as important in this, as you'll see in a minute. So it was seen by somebody else. And that started quite some piece of science. Because what happened here is, again, a picture of how well you can determine where something is. That's the sky. And here, these are the LIGO. This is the LIGO band. This is the LIGO uncertainty position on the sky, the two LIGOs. When you add in Virgo in a very spooky way, Virgo did not see this. But they were able to give information that allowed us where to look better. And the reason was because we knew Virgo worked. But the antenna pattern of these things has a null in it. There's a place where the antennas don't work. And it turns out that if they didn't see it, it must have been in that region where it didn't work. Imagine such an inference. But it turned out it was a very good inference. And that narrowed down the thing to be about there. That's now Virgo. We include that as a Virgo detection, a non-detection, but Virgo aided in getting this. And people looked there. They now had a place, and here's Fermi, by the way. That's the gamma ray telescope has this uncertainty. And then here, Indigo, which was, that's why it doesn't play much of a role. It was seen. And so here, then, is this, all the different measurements sort of focus on that in this region. And lo and behold, people about 8 hours or 6 hours later, using an honest-to-God optical telescope, saw a galaxy, NGC, whatever that's the 93. I don't care for the numbers. It's just a place, okay? And they saw this, and here's a picture they saw first, back a month ago. And here's the galaxy. And then here are stars that are around the galaxy, and that's pretty clean. But now come up here, and you'll see the same pattern of stars, but there's a new thing right about there. And that is this event. See? That was a very important thing, and that caused a lot of people all over the world with their telescopes to look at this thing. And here's what they thought they were seeing. And this is the model for it. Here's two neutron stars coming together. They smash together. They ultimately probably will make a black hole, and they emit this gamma ray burst. And they would do it this way, and this was gamma ray burst was seen a little off axis, and that was part of the modeling. And this picture isn't quite right. It's evolving every day. There's new information coming about this picture. People think a cocoon formed in here, and it made it so that there was less of the pulse coming out. It was self-absorbed in here. Let's not get into details right now. But this is called a killer nova, and it had some consequences, and here are the consequences. It was seen, as I say, by a lot of other people. And this is why it's called multi-messenger astronomy, and that's a big field now. And I know that you have a person I talked to at lunch who makes a specialty out of multi-messenger astronomy. And what's happened is that the National Science Foundation, which provides money for this, has made a center theme of what they're now looking forward to in the next 10 years. One of them is multi-messenger astronomy. So if you have ideas on multi-messenger astronomy, you might have a chance of getting funding. Okay? So anyway, what that means that you have a lot of different, it was seen by people in the infrared, people in the radio, people in, virtually every piece of the electromagnetic spectrum, as well as LIGO, but it was not seen yet in neutrinos. That's the vista. There will be others that are seen in neutrinos by that big experiment, which I think you're part of in the South Pole. Okay, so with that, several things were discovered. One of the first things I discovered, here's a little story. I have a little bit of time, so I'll say it. One of the puzzles, this solved two puzzles. The first puzzle I won't have more slides about, so let me start with the first puzzle. People had proposed, this is sort of a place where theory was way ahead of observation. Back in the 70s, or late 70s, Sriparam and Tran, these are two scientists, predicted what I'm about to tell you, namely that two neutron stars, when they collide, make all sorts of elements. That's a periodic table that you see there. Those of you who know chemistry have seen that and probably know it much better than I do. And what it is there was an idea early on in the history of thinking about how the elements got formed, that people said, well, all the elements, if you have this beautiful thing, we know all the elements, we know how quantum theory tells you exactly how this picture works, but we don't know how they actually got formed. And so in the early universe, very early universe, and we know the universe is expanding, and we know also that it was an explosion that started the universe. And so consequently, we know from the very beginnings of the universe that hydrogen, that's the element that's way up there, the easiest element to do anything with, and helium, which is over there, if I see things right, those were the two things that existed in the explosion, that got made in that explosion. And a few other light things, like lithium, very little bit of it, and a little bit of beryllium, but when they got to boron, which I have to find, right there, they couldn't make it anymore. There was no way to make boron. When people analytically looked at it. And so, in fact, the man who did a lot of this was George Gamow, and people around him. And they gave up on it because they thought with this idea of putting neutrons and protons together and adding all the electrons in the big explosion, they could explain the whole bloody thing. They couldn't. They got stopped right there. And so what then happened is that other people like Hoyle and the Burbages and Fowler began to think about where are the other elements made. It turns out the things that you and I are made of will come out of stellar explosions all over the universe, big supernova. So, but that quits just about somewhere where you can see there where all the yellow stops. The things that are green still made that way, but you can see it from here, dying low mass stars. They even tell you, so it's good. This is a picture straight out of Wikipedia, so you can get it yourself. And so what happens is that these purple guys, they couldn't get made. And they began, because I'll tell you why, they're heavy, and you need a lot of neutrons, and it turns out the hypothesis was that maybe these are made in collisions of neutron stars. And it turns out we think that's right. And part of what gives us that kind of evidence, I don't have the picture for it, is people looked with their telescopes at this thing and noticed that the way the light changed, the amount of light that comes out of that explosion, changes in a very specific way that tells you that very heavy elements are being made. I wish it was better than what I told you. It turns out I thought when I first heard this that people were looking actually at atomic lines of gold and silver. They're not. They were looking at opacities. That's a technical detail for some of you who care. Turns out it's not absolutely 100%. I think it's 90%, but there's 10% possibility in my mind that it's not. They even think that all the heavy nuclei, gold and uranium and all that, come from neutron star collisions all over the universe. The other thing that was discovered, and this is a very cute little piece, is that, and maybe this may be a little fast for you, but I can't help it, we'll get to things again, is that they were able to use the two neutron stars, and knowing that they were neutron stars, they were able to calculate, using Einstein's equations, the masses. We have ranges of the masses, and they were also able to calculate how strong the strain was in the detectors we measured. So they had two things. They had the masses, so they knew how much gravitational amplitude was radiated at the neutron stars. And you had a measurement made on the Earth for what the strength was at the Earth. What that gives you is the distance to the source. You know how the field, it turns out, there's a subtlety there, it turns out the signals you see drop as 1 over the distance, not 1 over the distance squared. And the reason for that is LIGO measures the amplitude of the signal. It's like the electric field that you saw in that demonstration. It doesn't measure the intensity, which is the power. It measures the amplitude. That's why you get so much detail out of the measurements of the waveforms. So those drop only as 1 over the distance, but that's a very tight relation. So you got the distance. And people also had measured the redshift, as they call it, the shift in the spectral lines in that galaxy whose name I didn't give a damn about, okay? And they knew where it was. They had a redshift that was known, and now they had a new way of knowing where it was. And that's what this picture is. See, here's that whole business of relating the redshift, which is the expansion of the universe's velocity, and knowing how the distance relates to it is given in something called the Hubble diagram. And here it is. This is the value that the two different experiments. There's an experiment that uses the cosmic background radiation, which is this, and another one which uses supernova. And here is the result, which is the result that came from this new way of doing it. It's not very good. We'll have more of these, but you'll notice it embraces what people are making a huge fuss about, the uncertainty difference between these two types of measurements. I wouldn't take that so terribly seriously yet. I know there's a hell of a debate about it, but look, no. So you can use even this one measurement as a beginning of cosmology. And it says that if you improve LIGO or keep at it, you will be able to make a major contribution to cosmology. Okay, so that's a thing. I just want to show this picture as a way of telling you a little about the future. I'll tell more to the people who I give a lecture to who are really interested in this, but this is a picture like all the ones you've been seeing, and this is a picture of the strain, and as things get poorer as they go up in this picture, you get better and better as you go down in this picture. And so here is the performance of Virgo. It's again frequency, here's 100 hertz, and this is strain. I just want to hear is the sort of performance of LIGO when we were making all the measurements that you now know about. And here's the measurements, here's what we wanted LIGO to be like here. That's the design for LIGO, right there, that line. And you'll notice it's not on. We still have a way to go. Here, that distance. At all these different frequencies to make LIGO work as well as we thought it would. So we've got a job to do still, even though we've made detections. And now, here's plans that people had. And why is this so important? Let me just say why it's important to get this right. It's important because the number of sources you might see, let's say the black holes or the neutron stars, if you can double the sensitivity of your instrument, because you can then, if you double the sensitivity of the instrument, make it twice as good, drop it by a factor of 2 in that picture, you can look twice as far. If you look twice as far, you're looking at a volume of the universe that's 8 times bigger than what you had before. So that means that if the sources are uniformly distributed in the universe, you will have 8 times more sources, 8 times more hits in your detector. That's spectacular. We're now getting something like 1 hit every month from black holes, 1 hit a year in the neutron stars. So if you improve that by getting even down to where we ought to be, we will get to the point where we're getting something like once every couple of weeks. And then if you get down to an idea that we already know how to do, which is again in LIGO, down to here, you're talking about events per week, or maybe even a couple of events per week. So it changes the character of the science completely. It's very different than looking all the time. That's the thing I'm trying to impress on you is that running all the time is not the best way to improve the science. One of the best ways, if you have a clever idea and make the detector better, that's generally worth doing because of this fantastic power law that goes with how many sources you will see. Okay, so I'm almost there. So, okay, now, the thing that's down in here, there are other ideas. This is another idea which I'll talk to the people in the gravity group about. This is sort of the last big step you can take, we believe, in the LIGO facilities. And then the next 2 curves, which are way down in here, which certainly bring this whole field into cosmology, are a projection for what there's a European plan for building a detector underground, which gives you this kind of curve. And then there's a plan which is much more embryonic. It hasn't been studied as much by the Americans to build a 40-kilometer-long LIGO. And we'll talk more about that tomorrow, those of you who care about this. So it turns out that those are all plans that people are thinking about. So the field isn't over, but you have to, unfortunately, spend money to make the next one. And that's part of the reason you ought to know some of the advantages of it. You may be in a position to influence that. Okay, so this is what happens if you now fill in the number of detectors that are planned in the Earth right now. Remember I showed you that picture of the 2 LIGO detectors and the Italian detector? There are plans, I don't want to bring the slide back. There are plans to build one in Japan called Kagra. There's one plan to build another one in India. That's LIGO India. And those things, which will probably happen in the mid-20s, will cause this picture, which is a picture of the sky, and forget about this extra H. That's a detector at Hanford, a detector at Livingston, and the detector Virgo. That's the three detectors. And this is sort of the sky, uncertainty in the positions of the sky for sources. Those big, for example, these bananas that you can't do, big areas that you can't do anything about. You add now LIGO India to that, and look what happens. It cleans up quite nicely, and you now have things that are more like the size of the moon. And that's one of the reasons why you would like more detectors distributed over the Earth. And that's what's going to happen in the 20s, we think. And this is my last slide. No, there's one after, but that's just for show. And this is now, what's the field up to? And this is now frequency. This is the frequency here's time up here, which I like better. This is 1/10 of a second to 1,000th of a second. This is where LIGO operates. This is H, the value of H associated with that. Here's LIGO. It gets down to small values of H, but it has in it very, very fast events. The next big project, and this will change as the place where this comes on this scale changes as we improve. But it doesn't change the frequency. We're not going to be able to change things much with the frequency. But if you want to look at longer wave periods from minutes to hours, there's a project that's been just as long in formation as LIGO to do this in space. This is called LISA, L-I-S-A, the Laser Interferometer Space Antenna, and it will look at big black holes colliding and looking at small things going into a big black hole, which have very precision tests for general relativity. And also it'll pick up white dwarf stars, which are quite ordinary. Many of them are in our own galaxy, and pick up the radiation from them. So it's an important project for the development of the science. There's another one you guys, I think, are mixed up with, some of you here. I know Sam Finn is mixed up with this. And that is using pulsars. This is now much, much longer waves, periods of decades to fractions of a year. And now what the idea there is to use pulsars that are all over the sky in our own galaxy and look for a pattern in their rates. In other words, here's the pattern. You look in the north, and all those pulsars in the north go a little faster than they did before the gravitational wave was there. You look in the south, and all of those guys are going a little faster. And you look east and west, and those two both are going a little slower. And so they're looking for things like that. We'll let you look for gravitational waves that are streaming through our galaxy with very long periods. And the final one over here is doing cosmology, and this is going on already. This is going on now, and this was going on even 3 years ago. People made a claim that they saw something. What this is probably more complicated to explain. I'll just tell you what it is, and if you could ask me, I'll explain it in detail to you if you care about it in the questions. The way it is you look at the cosmic background radiation, which is the radiation that comes from the explosion that the universe made at 14 billion years ago. And that radiation it comes from a plasma. That plasma is the source of the radiation that we now have. Was it for 10,000 degrees at the time when it was formed, and now it's at 3 degrees Kelvin. Okay, and what you see in that is that you see radiation coming at you. It's that same radiation that you radiate and you have to eat. That's the reason you have to eat, to keep hot. So you're at 300 Kelvin. This is at 3 degrees Kelvin. And what that radiation comes from is that big explosion. Now, everybody, a lot of people, not everybody, but many, many people think that the very instant when that explosion happened, there were a huge amount of gravitational waves generated by quantum fluctuations. The universe was a quantum fluctuation. It's a crazy idea, but it's not a bad idea when you think about it. And what happened, there were gravitational waves associated with the accelerations of those fluctuations. They made gravitational waves that have now persisted from that on and did something to the plasma of that made that 3-degree radiation, and what it did, it made density fluctuations in it of a certain pattern. And that pattern shows up in what's called the polarization of that radiation. I gave you a mouthful there. It's a lot of words, and if you want, I can explain it better. When those patterns of polarization, they're called B modes, and they make spiral patterns in the background of the radiation. If you look very carefully, those will tell you what the strength of the gravitations were at the time when the universe, a little bit at the moment, about 300,000 years after the universe was created. So, and that's just one last slide, but the talk is over. You're in that thing somewhere. This is a picture of the LIGO scientific collaboration. I don't know where to find you in there. You're in there someplace. You found it? Okay, good. Anyway, thank you very much. I'll try to answer. I'm not always possible, you know.
And then there are also few people with mics, so please don't start the question until somebody with a mic after that. There's a question over there, the last seat there.
So I just wanted to ask about the construction of the LIGO. You said that it has this sort of noise-canceling headphone thing where it compensates for disturbances in the Earth, let's say. Do you still have to go to great lengths to isolate LIGO from, or does that pretty much take care of? When it's built, does it have to be extremely isolated from the ground or from, are there other ways to?
Let me say that, if you ever played with trying to make an isolator, of any kind of motion, it's very hard to make a good isolator for low frequencies. What I mean by that, a low frequency isolator requires that you have a spring and a mass system that has a very low resonance frequency, or a pendulum that's very, very long and has a very low frequency. And that's the way you get the isolation. You have a system which is a resonance system which has a very low frequency. And it turns out they get terribly hard to deal with. To make isolation at 1 hertz is very, very hard. Because at 1 hertz, if you build a 1 hertz pendulum or 1 hertz spring system, it just amplifies all the noise at 1 hertz. It's a terrible way to do it. So it turns out you have to make what's called these active systems. But all the high frequency isolation, acoustic isolation and high frequencies, let's say from 10 hertz on up, it's all done by those pendulum. Okay? But it turns out so much of the noise, I don't know, those of you who have a seismometers here, I'm sure you have a geophysics department, go find out what the Earth is doing, and you'll find out the Earth is just terribly noisy at periods of 0.1 hertz and 0.3 hertz. It's because of what makes a lot of the noise here, for example, is the Atlantic Ocean. It's the waves that hit the shore, and that is devastating to us. So we have to make these active systems isolate even that far down. Okay? It's the best I can do for you. Okay.
So the neutron star collisions and black hole collisions that we detected from...
I can't hear you well. Where are you?
Hi.
Oh, there. Okay, good. Speak up.
So the neutron star collisions and the black hole collisions that you detected from LIGO, were they within our galaxy or not?
I didn't get the last part of your sentence.
Were they within our galaxy
Where's
or
what?
not?
Oh, I didn't tell you that. Yeah, you're absolutely right. You asked the right question because I was a dope. Okay, I should have put in that table of all the black holes. The black holes seem to be concentrated at about, that we can see because we begin to see them, at about 1.2 billion light years away. Okay, and we begin to see the one neutron star we've seen is about 120 million light years away. They're not in our galaxy.
Thank you.
Yeah, thank you for the question.
So I'm wondering, if you now begin to detect more and more and more of these events, either black hole mergers or neutron star mergers, could you maybe build some sort of statistics about like where these, where these events are located in the universe, and maybe make some sort of conclusions based on that?
I didn't get the last. I'm sorry, I was being disturbed, but that's it. Thank you. No, what was the question you asked? I know about the black holes, and you want me to say something about it.
Right. So
say it again, please, louder.
I guess what I'm thinking is, if you get enough detections, can you start making some inferences about why more or less events happen in certain regions of the universe, or something like that?
Okay. You're asking the distribution, okay.
Yeah,
I think that's what you're asking. Let me say we don't know much about that, and that's one of the reasons we clearly have to make a better instrument. Let me give you a little bit of people who are in the group here. If you want to learn more, come and talk to the gravity people here, who are first class in this business. And that is that, for example, I'll give you the black holes. When we began to see them, people didn't, first of all, they were anomalous in the sense that people had always before this seen black holes which were much lighter, sort of 2 or 3 solar masses, maybe 4, up to 10. But all of a sudden, when we got into this business, we got to see these big, heavy guys. And they make even bigger ones when they crash together. So that was quite anomalous, that people have never seen them really in any kind of other astronomy. And so we people began to think, all of us began to think, where did they come from? And we still don't know for sure, but there's several ideas about it. There are 3 at least. One of them is that they get generated when big stars collapse, like other black holes are, but these have to be big, big stars, monster stars, hundreds of solar mass stars. Could be, and those are called common envelope formation. And we hope ultimately to determine if that's the way, by looking, for example, at the spins of the black holes. And we don't know how to do that yet. We don't see, we're not sensitive enough to pick that up. But if you have common envelope, it comes from one collapse of one big, big star, that spinning of the two black holes would probably be in the same direction. They'd be spinning the same way. On the other hand, there's other places where this could happen. They could happen in something called globular clusters. These are things which are all over our galaxy and most other galaxies, especially spiral galaxies. And these are places where the number of stars formed per unit lifetime of the universe is unbelievably big. You have maybe 30,000 stars all living together in a tiny little region. And it turns out those places, it could be just from collisions that you got all these black holes. So those would favor probably that the spins don't align with each other, okay? We don't know that. And then there's a subset of people who think that these are actually products not of stellar collapse, but they're geometric devices. They're things that come from the geometry of space-time at the beginning of the universe. Now, I think that's very unlikely, but you can't rule it out yet. In other words, that they are primeval objects. So now it's very important, in order to determine this, to get the detector better, so we can start measuring some of these things. We can see the spins. That's very important. We can see what the distribution is throughout the galaxy, throughout the universe. For example, if they're known after a certain z, a certain distance away from the Earth, that'll tell you right away they're not primeval ones. They must have been generated by stars. So anyway, all sorts of wonderful questions have arisen out of this, and I can't answer them. And that's the question they're asking me. Neutron stars are almost certainly made from the collapse of other stars. And they're distributed all over the universe and when was the first star made? That's a question that a lot of people think at a z of something like 10, 15, you have to make stars first before you can make galaxies. And that, by the way, will be heavily looked at if James Webb, the big telescope that keeps being in financial trouble, ever gets off the ground. James Webb will look deep enough because it has infrared capability to look at the formation of the earliest stars. So will people looking at the 21 centimeter tomography. That's something maybe you don't know about, but it's a big development in radio astronomy, is to look at the hydrogen hyperfine structure line at different epochs. It'll always be at different frequencies, and look deeper and deeper in the universe. At some point or another, that hydrogen will look like it's not hot enough to radiate, and you will see that that's the place where stars got, at the place where it's still hot enough to see it, it's still the place where stars are made. If it cools down too much, it's too early. So that'll give you a sharp place where when the first stars were made. So those are questions that are all ahead of us. It's just wonderful science that's going to happen.
Yeah, you had said there early on that the gravity waves travel at the same speed as light. So why is it the case that when we saw the two neutron stars, we saw the gravity wave signal before we saw the gamma
Okay,
wave?
that's a good question, but I think it's too easy to answer that. Remember, the thing is it's like 120 light years away. It takes, in a year, there's 10 to the 7 seconds. 120 million is 10 to the 8. It's 10 to the 15 seconds in travel. Both the gravitational wave and the gamma ray travel together to us. It took us 10 to the 15 years, 10 to the 15 seconds to get us to us. And they were only different in time, right, less than 2 seconds. You make that calculation and say, my God, they're equal in velocity 2 apart in 10 to the 15. That's the easiest way to get the velocity of gravitational waves. There are other ways to get it, and people who are very subtle in their data analysis, and some of that was done here, is that they looked at the wave shape, very carefully the wave shape of the black holes. And since you now can do the analysis of the black hole and get the wave shape to be matching the data, you can use the fact that the different frequency components, that are the different frequencies, you saw it went from 30 hertz up to 256 or to 300 hertz. The different frequency components will travel at different velocities if the velocity of gravitational wave is not the velocity of light. That means that the particle we call the graviton, which is a quantum principle, but that it says that particle doesn't have a zero rest mass, which means it isn't going at the velocity of light. So we already knew before we saw the neutron star, and I don't know the exact how well we knew, maybe Abe knows, but how close the velocity of gravity had to be to the velocity of light. But we already had a pretty good instinct about that alone from the gravitational, from the black hole collapses. Is that the question you asked? How do we know that the times are the same? Yeah. It's a pretty good, look, I think that's the wrong place to worry at right now. I think we got that one nailed. Yeah.
Sorry. Hello.
Hi.
So you showed us a visual model of gravitational waves, and I noticed they were only like on the bottom of like the object in question. So I was wondering what they would look like in a 3D model, or like
Okay,
how,
you asked a wonderful question.
yeah, like how they affect other things next to it.
Let me tell you, I lied to you. Okay, I mean, you have to accept that. To make it so I could at least get this. It turns out if I'd shown you the whole thing, I would have to show you that same diagram, but turned by 45 degrees. You know that diagram? You had the stretching this way and compression that way, and then it flipped. Okay, there is another polarization to gravitational waves. They're completely independent of each other, which if you turn that whole picture by 45 degrees, and then you have stretching this way and compression that way. And again, inverting. So it turns out two polarizations, like you do with light. There's two polarizations also. And it turns out that you can make out of those two polarizations, you can make waves that rotate, circularly polarized light, circularly polarized gravitation. You need those degrees of freedom to do that. So I lied to you. The three-dimensional picture would have looked much more complicated than that one. I would have had to include both polarizations in the whole bit. Thank you. Yeah.
Okay, so Ray is going to give us a much more technical seminar about the future of gravitational science on Friday in Whitmore at 10 o'clock.
In here? Really?
Not here.
Oh, upstairs, yeah. Okay, yeah. Jeez.
And also this very students from Canada here, they know about gravitational waves very well. They work actually, some of the slides that they showed, the names that are here, they are actually students here who did all that work. So therefore, I have a lot of expertise here. So those of you who would like to know more about it, please contact people who are studying the analysis or so forth. And also who are sitting here, and they will be able to get that forward. So let us thank Ray again.